Good day, everyone. Today we are going to discuss one of the most powerful forecasting tools used in business, economics, finance, marketing, public policy, and data analytics. That tool is called Time Series Regression Models. Now, before we begin, let me ask you a simple question. Have you ever wondered why some businesses seem to know what will happen next? How does Starbucks estimate future coffee sales? How does Amazon forecast online orders? How does Tesla estimate future vehicle demand? How does the Federal Reserve predict consumer spending? How does Netflix forecast subscriber growth? The answer is that many of these organizations use regression models. Regression models help us understand relationships. They help us answer questions like, if income rises, how much will spending increase? If advertising increases, how much will sales increase? If unemployment rises, what happens to consumer demand? If interest rates increase, what happens to home purchases? Regression models help us move beyond guessing and toward evidence-based forecasting. Today's lecture will teach you how regression models work, how they are evaluated, and how businesses use them to make decisions worth millions or even billions of dollars. Why regression matters. Imagine you own a small coffee shop. Every day you notice something interesting. When the weather gets colder, coffee sales increase. When the weather becomes extremely hot, cold drink sales increase. You start asking yourself, can weather help predict sales? The answer is yes. Weather becomes a predictor variable. Sales become the variable you want to forecast. Regression is simply a mathematical method that measures the relationship between them. Instead of saying, I think sales will go up, you can say, for every 1 degree drop in temperature, coffee sales increase by approximately 5%. That is the power of regression. It converts intuition into measurable relationships. 7.1. The linear model. The simplest regression model is called the linear model. The idea is straightforward. We assume that changes in one variable produce predictable changes in another variable. Imagine a university bookstore. Suppose the manager notices that every semester, when enrollment increases, textbook sales also increase. After analyzing the data, they discover, for every additional 100 students enrolled, textbook sales increase by approximately $15,000. This relationship can be represented by a straight line. The regression model tells us sales equals starting value plus impact of enrollment. Think about another example. Suppose you are a landlord. You own several apartment units. You discover that larger apartments rent for higher prices. Every additional 100 square feet increases monthly rent by $250. Again, that is a linear relationship. As apartment size increases, rent increases. Regression helps quantify exactly how much. The model contains three major components. First is the intercept. Think of the intercept as the starting point. Imagine Uber drivers. Even before they begin driving, there may be a base payment for showing up. That starting value resembles the intercept. Second is the slope. The slope tells us how much the forecast changes when the predictor changes. For example, if every additional advertising dollar generates $5 in sales, then the slope equals 5. The slope is often the most important part of a regression model because it measures influence. Third is the error term. Students often misunderstand this. The error term is not a mistake. It represents all the things we cannot explain. Suppose we predict restaurant sales based on temperature. Even if temperature is important, many other factors still matter. Traffic, special events, competition, road construction, social media reviews. The error term captures everything not included in the model. Real-life example, consumer spending. One of the examples discussed in the chapter involves consumer spending. Think about your own life. When people earn more income, do they spend more money? Usually, yes. When people lose jobs, do they reduce spending? Usually, yes. When people become worried about the economy, do they save more? Often, yes. Regression allows economists to measure these relationships. The chapter shows that income has a positive relationship with spending, while unemployment and savings have negative relationships. This makes intuitive sense. People spend when they have money. People save when they are uncertain. People cut spending when unemployed. Why multiple regression is better. Suppose you are trying to predict a student's GPA. Would study hours matter? Of course. But is GPA determined only by study hours? No. Sleep matters. Attendance matters. Motivation matters. Health matters. Previous academic preparation matters. A model using only study hours would miss important information. A multiple regression model includes several predictors simultaneously. This usually improves forecasting accuracy. The same principle applies in business. Sales are not driven by only one factor. Most business outcomes have multiple causes. 7.2, least squares estimation. Now let us discuss how regression finds the best line. Imagine you have a scatter plot of points. The points do not form a perfect straight line. They are scattered. The question becomes, where should the line go? Regression chooses the line that minimizes errors. Specifically, it minimizes the sum of squared errors. Why square the errors? Imagine two prediction mistakes. One error equals 10. Another error equals -10. If we simply add them together, they cancel. The total error becomes 0. That would be misleading. Squaring prevents cancellation. Large mistakes receive larger penalties. This encourages the model to find the best possible fit. Think of a basketball player practicing free throws. The goal is not to hit close to the basket sometimes and miss badly other times. The goal is consistency. Least squares works the same way. It finds the line with the smallest overall prediction errors. Understanding R squared. One of the most popular measures in regression is R squared. Think of R squared as an explanation score. Suppose a professor predicts student grades. If the model explains 80% of grade variation, then R squared equals 0.80. The remaining 20% comes from factors not included in the model. Consider sports. Suppose a baseball analyst predicts team wins using payroll. If payroll explains 70% of winning variation, then R squared equals 0.70. That does not mean payroll causes all success. It simply means payroll helps explain much of the variation. Higher R squared often indicates a stronger model. However, a high R squared alone does not guarantee a good forecast. We must also check for other problems. 7.3, evaluating the regression model. One of the biggest mistakes analysts make is assuming a regression model is automatically correct. It is not. Regression models must be tested. Think about buying a used car. You would never purchase it without inspection. Regression models deserve the same scrutiny. One important tool is residual analysis. Residuals are simply prediction errors, actual value minus forecast value. If residuals show patterns, something may be wrong. Imagine throwing darts. If all darts consistently land left of the target, you have a systematic problem. The same principle applies to forecasting. Errors should appear random. Patterns indicate missing information. Outliers. Now let us discuss outliers. Imagine a class where most students score between 70 and 90. Then one student scores 5. That score is an outlier. Outliers can dramatically affect regression results. Suppose you study income and spending. Most participants earn between $30,000 and $100,000. One participant earns $50 million. That single observation could distort the entire regression line. Analysts should always investigate outliers. Sometimes they represent real phenomena. Sometimes they are simply data entry errors. Spurious regression. This is one of the most important concepts in forecasting. A spurious regression occurs when two variables appear related but are actually unrelated. For example, ice cream sales increase during summer. Drowning incidents also increase during summer. Does ice cream cause drowning? Of course not. Temperature causes both. Temperature is the hidden factor. Another famous example compares Nicolas Cage movie appearances with swimming pool drownings. The correlation appears surprisingly high. But there is no causal relationship. Correlation alone is not enough. Always ask, Does the relationship make logical sense? 7.4 Useful predictors. What kinds of predictors should we use? The chapter identifies several useful types. Trend captures long-term movement. Think about smartphone adoption. Over many years, usage generally increased. That long-term increase represents a trend. Think about online education. 20 years ago, online degrees were relatively rare. Today, they are mainstream. The long-term growth pattern is a trend. Including trend variables helps capture these changes. Dummy variables. Suppose you own a toy company. Sales spike every December. Why? Christmas. The month itself matters. Dummy variables allow us to represent categories like seasons, holidays, or promotions. Another example. A restaurant may experience higher sales on weekends. Weekend and weekday categories can be represented using dummy variables, Fourier terms. Now imagine forecasting electricity demand. Demand follows seasonal cycles. Summer air conditioning usage rises, winter heating demand rises. Fourier terms help model repeating seasonal patterns efficiently. Distributed lags. Some actions create delayed effects. Advertising is a great example. Suppose Coca-Cola launches a national advertising campaign. Consumers may not buy immediately. Some purchases occur weeks later. Distributed lag models capture these delayed responses. Australian beer example. The chapter discusses Australian beer production. Think about beer sales. Do people drink the same amount every quarter? Probably not. Summer consumption may differ from winter consumption. Holiday periods may increase demand. The model captures both trend and seasonality. This is exactly why businesses love regression. It helps separate multiple influences simultaneously. 7.5 Selecting predictors. Now comes a critical question. How many predictors should we include? Many students assume more predictors automatically mean better forecasts. That is not always true. Imagine hiring employees. Would you hire every applicant? Probably not. Some candidates contribute value. Others add complexity without benefit. Predictor selection works the same way. Adding unnecessary variables can create overfitting. An overfit model performs well on historical data, but poorly on future forecasts. It memorizes the past rather than understanding it. Think about a student who memorizes practice exam answers without understanding concepts. When the actual exam changes slightly, performance collapses. That is overfitting. Regression models can suffer from the same problem. 7.6 Forecasting with regression. Now we arrive at the ultimate purpose of regression, forecasting. The chapter distinguishes between ex post and ex ante forecasting. Ex post forecasting uses known historical information. It helps evaluate model performance. Think of it as replaying yesterday's football game and seeing whether your predictions would have been correct. Ex ante forecasting predicts the actual future. This is what managers care about. What will sales be next quarter? What will inflation be next year? What will enrollment be next semester? Those are ex ante forecasts, prediction intervals. Forecasts should never be presented as single numbers. Every forecast contains uncertainty. Suppose I forecast sales next month will be $100,000. That sounds precise, but reality is uncertain. A better statement is sales next month will likely fall between $90,000 and $110,000. That range is called a prediction interval. Weather forecasting provides a perfect example. Meteorologists rarely say, tomorrow's temperature will be exactly 72.4 degrees. Instead, they provide ranges because uncertainty exists. Business forecasts should do the same. 7.7 Nonlinear regression. Not every relationship is linear. Imagine exercise and happiness. Initial exercise improves happiness significantly. However, after a certain point, additional exercise produces smaller benefits. The relationship bends. It is nonlinear. The chapter discusses log transformations. These are especially useful when percentage changes matter more than absolute changes. For example, if a company's sales increase from $1 million to $2 million, That is very different from increasing from $101 million to $102 million. Log transformations help capture proportional relationships. 7.8, correlation, causation, and multicollinearity. This section may be the most important in the entire chapter. Repeat after me. Correlation does not imply causation. Just because two variables move together does not mean one causes the other. Suppose shark attacks increase during summer. Ice cream sales also increase. They move together, but neither causes the other. Temperature influences both. Always search for underlying explanations. The chapter also discusses multicollinearity. This occurs when predictors contain similar information. Imagine interviewing identical twins about the same event. You receive nearly the same information twice. The second interview adds little value. Predictors can behave similarly. When variables overlap too much, coefficient estimates become unstable. However, forecasting accuracy may still remain strong. The biggest problem arises when analysts try to interpret individual predictor effects. Conclusion. As we conclude today's lecture, remember these key lessons. Regression models help us understand and forecast relationships between variables. The strength of regression lies not simply in prediction, but in explanation. We learn which factors matter. We learn how much they matter. We learn how future changes may affect outcomes. But we must also remain cautious. A high R-squared does not guarantee truth. Correlation is not causation. Outliers can distort results. Spurious relationships can deceive analysts, and overfitting can create false confidence. The most effective forecasters are not those who blindly trust models. They are those who understand both the power and the limitations of those models. Regression is not magic. It is a tool, and like every tool, its value depends on the skill of the person using it. Thank you, everyone. In our next lesson, we will continue exploring advanced forecasting techniques and how organizations use data-driven models to improve strategic decision-making in an increasingly complex business environment.